Hello class, in this video we're going to be looking at engineering drawing standards. So in your textbook we're going to be starting on page 1 and going through page by page. You can also look at my presentation files, the PDFs, on the Moodle site. So let's have a look at our drawing page sizes first of all, so that we become familiar with those. All right, so you may all have come across an A4 page before. This is the most common, everybody knows it. Most printers are designed to print on an A4 page, unless you're in America and they print letter sizes and various things. But as we know, the Americans are always different, sticking with inches instead of millimeters. But yeah, the A4 page is probably the most common. But there's actually a range of page sizes in the metric page size range. So if we look at an A4 page, if we take two of them, and what I've done is I've put an A3, I've put a page on my drawing board, but let's just take this one for example. This is an A3 page. You might have come across an A3, so you see it's a bit bigger than an A4. But if we take an A4 and we line it up with the edge like that, you'll see that the height is exactly the same. And if we take another A4 and we put it next to that one, we will see that it ends up being exactly the same size as two A4s. So essentially what we're doing is we're doubling up or halving every time we go up the A numbers. So we've got A4, and then we've got A3. As the numbers get smaller, the pages get bigger. So this is an A3. If we had to take that A3 and put another one next to it, then we would get an A2 size, and now we're getting bigger than my screen, so I can't go any bigger than that. So you've got A2, you've got A1, which is double A2, and A0, which is double A1. All right, and then if we look at the other direction, if we take our A4, if we want an A5, we just have to halve it. So we can fold it in half, and now we have an A5 size. We fold that in half again, then we'll get an A6, and probably an A7, etc. All right. So hopefully that explains to you a little bit more clearly what we're talking about when we are talking about A size pages. All right. So for the engineering drawing boards that we use, we're mostly drawing on A3 pages because it gives us a nice size to use all our drawing equipment effectively. All right. So the next thing we want to talk about is scales, and I mentioned it a little bit in the introduction video, and that is we often draw things as engineers that are a lot bigger than our page size that we have. And you may remember from the last video, this is my scale ruler, getting quite old now, but it's still effective. And this one allows me to draw to scale without doing the calculations in my head. So if I want to draw something that's half, on the page it's going to be half the size of real life, then I will use a 1:2 scale. So if I measure 100 millimeters, which is that over there, let's just do that now. So if I take my pencil, we lock our ruler in position, and I draw a line, and let's measure on my scale ruler from there to there. That says 100 millimeters on the scale ruler. But if I flip it over, I go to 1:1 scale and I measure that, then it shows me 50 millimeters. All right, so that the actual size that I drew is 50 millimeters. But if I say on the side of my drawing, I say scale is 1:2, then that will be 50 millimeters on the page, but it'll be 100 millimeters in real life. So what I could do then is draw a dimension. So engineering drawings also have dimensions. Let's just draw a quick dimension line like that. You want your arrows to be nice and long and thin. So with a scale of 1 to 2, what we did was we measured 100 millimeters. So we would write 100 millimeters. So our drawing will always show the number for the actual size. All right, so let's not get confused there. The only thing that's happening is that the size of the picture is shrinking to fit on our page, but the numbers that we write down will be the true size, even though it says 1 to 2. All right, what that also allows us to do is, if we have a certain shape, a certain curve, and we've got a scale on there, we could create a template from that shape and use that for the construction of something. So that's also quite useful, and that's called scaling of a drawing. That is, if it's drawn full size, which is 1-to-1 scale, we can actually trace it off and use that to create something. But it's not advised usually, because your paper is subject to temperature and humidity variations, which then the paper expands when it gets very high humidity. Like when it's raining outside, the air will be very humid, and the paper will absorb that humidity, that moisture in the air. And then the wood fibers in the paper, it's made from wood, that will expand slightly. So on an A0 drawing, across the paper you might expand 2 to 3 millimeters or maybe more, with fluctuations in humidity. So that means that it's not a good idea to actually measure the size of the drawing, assuming that the paper is correct. So just be aware of that. All right, so that is what a scale is. So a scale is essentially allowing us to draw something much smaller to fit the page size, especially if you're in civil engineering. You're going to use very large scales like 1:200 or 1:1000 even, because you're drawing bridges and buildings which are very large and you want to get them on your page, but you still want to draw them to scale. For mechanical engineering and industrial, we tend to use smaller scales, so like up to 1 to 2, 1 to 5, 1 to 20, 1 to 50, because our machines don't tend to be that large. Maybe marine engineering would actually need to use quite large scales as well, because if you're drawing a whole ship, then that ship has to fit onto your page, depending on what part of the ship that you're going to be building. All right, so that is what the scale is. Just in case you're thinking about how does it work in CAD, which is computer-aided design, you always draw everything full size. So that's 1-to-1 scale. So all your dimensions are 1-to-1 in CAD, because there's an infinite size inside the computer to draw in. But when it comes to printing that drawing on a page, you would format an A3 page and you'd give it a scale, and it would take your 1-to-1 model, 3D model, and it would shrink it down to fit on the page, so that scales are still relevant even when it comes to CAD. All right, so that's all I'm going to say about scales for now. Let's start having a look at line styles. Okay, so engineering drawing is all governed by SAB's standard, which is the South African Bureau of Standards, which I think they've changed to SANS. So all of these things I'm going to be showing you is all documented in an SANS standard, South African National Standards Organization. When it comes to dimensioning, tolerancing, first angle projections, projection symbols, etc. That is all documented. And the reason for that is it's like a dictionary for drawing language, because what we're doing is we're learning a new language. It's a visual language. It's a way of communicating. So just keep in mind that engineering drawing is a communication language, and we have to speak clearly, which means we have to use the right words, we have to use the right lines, we have to use the right techniques and show things in the right way, so that a person anywhere in the world can look at it and they can understand it, and they can actually manufacture what we've drawn on the paper or in the CAD. So that's why the engineering standards are so important. All right, so let's have a look at the different line styles. There's quite a long list of line styles, and in your textbook, we're now on page 3. Here we've got a whole variety of line styles. I'll just show you how they work. If we start off with a line style of A, then we have a thick line. Let me just get a ruler here. A slightly longer one will work nicely. All right, so let's just draw a line A. So that will be a solid line. That will be a thick continuous line, usually 0.5 millimeters. And that is for visible outlines and edges. So you start off your drawing by doing construction lines, which are very thin and very light, and then you draw afterwards. You go around and you make your edges darker, so that the edge of the part of the drawing stands out, because it's nice and dark. So just be aware of the need to make some lines dark, some light, so that you can highlight things. Okay, so that's line A. Line B is a thin continuous line. So I'm going to use the same pencil, but not press as hard. They say you should be drawing in 0.3 or 0.35 if you've got a pencil like that. But as I said, you can manipulate your pencil and create different line weights with a single type of pencil. All right, so that is a thin continuous line. So this line is used for dimensions. So as you can see, I drew a dimension line there. It's a very thin line. Leader lines, which are the ones that come out from the part to show you where the dimension starts and ends. Also hatching, if you're cutting through a part and you need to show hatching lines, I'll talk about that later. Outlines of revolved sections, bending or folding lines, or short center lines. All right, so that is a thin continuous line. It's also kind of a construction line. All right, C. Line C. There's two types, and that looks like something like this, and that is a thin, continuous, irregular freehand line, 0.3 millimeters, and that is if you are, let's say you've got a long part, and you like a railway line, and you don't want to show the whole railway line. You want to show the start and the end. Let's just draw the top of the railway line. It's got that thicker section, and the bottom has a flange. And you want to dimension it from end to end with a thin line. So here's our dimension. But you don't want to use up your whole page because it's a really long railway line. So you just want to show a portion, like the beginning and the end of the part, and then dimension it. But then you want to show that there's a break. So we can use this break line like that. Do it on both sides. So I'm just showing that that is a broken section. That is not, let's say that's 2,000, so that's 2 meters long. So that shows that the length of this part on the page is not to scale. It's got a break. It doesn't mean you've really broken the part in real life. It just means that on your drawing you're showing that it is not its true length. You can also do that that line that's got that interesting shape to it, which looks like your heartbeat on a heartbeat monitor. So that's also another way of doing it. So that is a second option for line C. All right, so then we've got line D, which is thin, short dashes. All right, so let's draw line D. We draw them thin and we draw them consistently. Yeah. I need to draw a little bit more consistently, but that would be also 0.3 millimeters, and that is a hidden line, hidden detail. So for example, we are drawing a part, but it's we're looking at it from the one side, but on the back it's got information that is useful to us. Then we will we'll draw the part as though it's transparent. It's like it's made out of transparent plastic, and then you can see through, you can see the lines on the other side. So you'll draw those dashed lines, line D, to show the information at the back and also indicate that it is not part of the front of the drawing. All right, then we go to line E, and line E is a chain dotted line. Okay, let me draw this side. Chain, so it's a long dash and a short dash, long, short, long, short. And so we go on, we try and be as consistent as we can. Also 0.3, very thin, and that is a center line. So if we're drawing a circle, let me just draw a quick circle here with my compass. And I want to show where the center is. I'll put a small cross in the middle to show that that is the middle of my circle. But then I will show center lines as a chain dotted line going out from there. All right, so that is my center line. I've drawn it a little bit dark here. Normally it would be light and then your circle would be darker. If I had to draw a side view, let's say that is a pipe or a tube, and I had to draw it, I'm just going to draw it smaller, and not very accurately. But if I did that, and then I went like this, that tells you that that is a circular cross section. So if you look at it from the end, it'll be a circle. If we don't put the center line, then it's probably a square. So that gives you some information that you wouldn't know otherwise if you don't have a side view. All right, center lines are chain dotted lines. All right, F. This is a cutting plane. So a cutting plane would look like a center line, except at the ends you would make them darker. And usually you would have like an arrow pointing to that. And then AA. So that would be a cutting plane, which we'll get to later on when we talk about sections. So that's cutting right through the part. Then you'll show another view with hatching on it. But that's basically a center line in the center, but on the edges you've got the darkened section and the arrows pointing to them. So that is F. Here we've got G, and G would be similar to a center line, except now we've got two dots. and that is an outline of an adjacent component, alternative and extreme positions of movable parts situated in front of cutting planes. All right, so if we've got a lever that's moving from one position to the other, we'll draw it to one position, and in a chain dotted line, we'll draw the alternative position of the lever, for example. All right. Line H looks like a center line, but it is just very much darker. And that is 0.5 millimeter. This is 0.3 millimeters. So that's for special requirements on surfaces. Don't use that very much. All right, so those are the main types of lines. Now if you go to your page 5 in your textbook, you'll see that there's a very interesting illustration here which shows you all the different line styles in one drawing. So if we look for A, we will see there's an A here, there's an A there. So those are the outer lines, the outlines, dark continuous lines. And we've got B, which is thin lines for hatching, for dimensioning, hatching again for extension lines. We've got C, there's your irregular cutout. And here as well, C2, remember those, like the heartbeats. There it's showing them there. And then we've got D, which is a hidden line. So you can see the top of the part is behind the lever. So therefore it's shown as dotted line where it's behind this part. Okay, E are center lines, chain dotted lines. There you can see the path of the center going there. Here's the center line there, center line there. So that's showing the center of this lever because it's symmetrical. And then we've got F, which is our cutting plane, as you can see there, and there we've darkened the edges. XX is a sectional view. So here we've got section XX showing the information that we're cutting through in that view. We've got G. Here's a double dot chain dot line. So this is like an alternative part. So this whole bracket bolts onto a table, which is shown in the double dotted chain line here. So the table is not part of this engineering drawing, but it's shown just to give you more information about where it goes. All right. If we also look at this line here, this is a double dot chain dotted line. That's an alternative position. The lever moves from there to there. All right. So there's all of the different lines illustrated for you nicely. All right, so the next thing we're going to do is we're going to look at the different types of lettering that we do on an engineering drawing. I'm just going through all of my slides to make sure I haven't missed anything. So if we look at lettering in the textbook here, you can see that we've got large letters and small letters. And the interesting thing is that they're all capitals. So on engineering drawings, we don't write in lowercase, we write in capitals. I know that's not the way that you learn how to use WhatsApp and type emails and so on. And it doesn't mean you're shouting. It just means that we're doing an engineering drawing and we're doing all of our letters in capitals, just to eliminate any confusion about the different letters and the different words. All right, so for practice, we're going to just do draw some letters. So normally for our for headings, let me just draw a nice line, a horizontal line here. For our headings, we will draw in 7 millimeters high So let me measure that. That's 7 is there, and I think it's 5 millimeters. No, titles are 5 millimeters and dimensions are 3 millimeters. Okay, my apologies. There's 5 millimeters and 3 millimeters. I'll just mark that out here. 5 millimeters and 3 millimeters, and we can just draw a line. Oh, that's not that one, it's the next one. Alright, so our title would be 5 millimeters high, and our dimensions 3 millimeters. Not the neatest, but we're getting there. Right, dimensions would be mostly numbers. So you need to practice writing neatly in the lines. All right, so it feels like we're going back to primary school, but it's important that we write neatly on our drawing. So do some practicing. There are some practicing exercises for titles and for dimensions. Right, the other thing we have to learn how to draw is our projection symbols. Now, projection symbol is important because it tells us how we're constructing this engineering drawing. So if I take this box, for example, and I want to do an engineering drawing, I can draw it from 6 possible views. So it's cube has 6 sides. So we've got a top and a bottom, we've got a left and a right, and we've got a front and a back. So that's 6 sides. Usually, if we're going to do orthographic projection, that's when we look at it from one side, and then we look at it from the other side, and then the third side. Usually we can describe the whole part in 3 views, or even a sectional view, sometimes even 2 views. We don't have to draw all 6 because we can put enough information. But it's important to show on your drawing which side you're looking at and how you're representing it. All right, so the symbol that we use, I'm not going to draw it to scale. The symbol that we use is actually a little cone. So I'm just going to draw a little 3-dimensional view of it so that it look like that. So this would be the center line through the cone. So that's kind of a sort of an isometric view of the cone. If we had to draw that cone from the front, from this direction, it would look something like that. If we had to draw it from this view, it would look something like that. Hopefully you agree. And there's my center line. And that is the projection symbol that we use. So what I've done here is I've constructed a small orthographic projection view. So orthographic projection is simply drawing something from on a flat plane from a particular view, and we decide which is the front, and we draw that as the front. Then we have a top, a left, and a right, and a back, and a bottom. But we need to tell people who are looking at our drawing how we've laid these views out. All right, so for this 3-dimensional cone, in this case, I'm looking at this cone from the left-hand side. If I'm looking at that view from the left, and I'm drawing it on the left, that would actually be 3rd angle projection. If I had to draw it this way around, and draw the circles there, and that's probably very small on the screen, but hopefully you'll get the idea. So now I'm looking at this view from the left, and then I'm doing it up and I'm drawing it on the right hand side. So that is first angle projection. Alright, so you can see the front view is the same, the side view is the same. It's just I've flipped over the positions of them. So that's the only difference between first angle projection and third angle projection, is the positioning of the views. The actual view would be the same. So in South Africa, we follow first angle projection as our standard. In America, they use third angle projection, but you'll come across both as you work in various companies. So the difference between first and third angle projection is the positioning of the views. With third angle projection, you draw the view that you see on the same side as your point of view. So your point of view is on the right, so you're looking that way, and you draw the right view on that side. So in this case, we're looking from left to right, we're looking at the right view, and we're drawing the right view on the opposite side. Just take that out of the way. So in first angle projection, our point of view is opposite to the positioning of the view we're looking at. So we draw the view on the opposite side. Okay, hopefully that'll get clearer as you move along. The most important thing is that we show that symbol on our drawings. So if I do an engineering drawing, I need to then, using my circles, I need to draw it neatly. For South Africa, we will do a first angle projection symbol, which essentially looks like that. You will draw it neatly with your equipment. So that's first angle projection. All right. So the next thing that we want to look at is sectional views. And doing dimensions. All right, so I think I need to put a new page on my drawing. I'll turn this one around, possibly, just to get some more space. That in there. So let's talk about dimensioning first of all. Alright, so dimensioning is arguably one of the most important parts of an engineering drawing, because it doesn't really matter what your part looks like, the picture. What people need to be able to manufacture that drawing is the sizes, the true size, the dimensions. All right, so if we are drawing a part, so let's just draw something rectangular. Not very neat, but it's going to have to do. and I want to dimension this part. What I will do is create leader lines. A leader line starts just beyond the part and moves away from it. It's a very light line. And then I'll do dimension lines. And dimensions are always, the larger ones are further out and the smaller ones are closer. Okay, that one wasn't long enough. Just extend it a little bit. So let's put our arrows, make them nice and long. So let's say that's 65 millimeters and this one is 45 millimeters. So you can see I put the number in the center of the arrow. So it's easy to see that that number belongs to that arrow. The 45 is in the center of that arrow. And the smaller dimensions are closer to the part. If I had to put that further out, the leader line would cross over and create confusion over where that 65 starts and ends and where the 45 starts and ends. So we don't ever cross over our dimensions. Now if we go to dimensioning this side, our leader lines do cross over. However, our dimensions don't. So here is our arrow. We can do it like this. And then there's two ways of doing it. We can either write all the numbers vertical, or we can turn sideways and write them. But yeah, it doesn't really matter. That's 20, and actually that's not 20, that'll be 40. I'm just sticking to the picture in the book. So that would be 40, and that would be 20. I would actually have to do another dimension here. 10. All right. So what is this size? And why don't I show it there? If I take the 40 and I subtract the 20 and the 10, I get another 10. So I know I can calculate that that is the 10. So if we had to put the 10 dimension in there, we are over dimensioning our part. So we're showing more information than we need. And then we're also making the drawing a lot more busy and cluttered than it needs to be. So the same with this side. We've got 65, we've got 45. We subtract those two to get this dimension. We don't have to put that dimension in. So that would be over dimensioning the part again. I don't have to show the 40 on this side either, because it's the same as that side. The sides of the part are parallel. So I don't draw those in. Okay, so if our part had additional steps in it, so let's just draw a few steps in here. Just join those up. And now we want dimension on this side. If we put dimensions on each of these steps, then to mark that out, we're going to be measuring from this reference, then from that one, and then from that one. And we're going to start accumulating errors in our measurement. So in this case, it is better to dimension from a common reference point, from a datum. So let's pick this as our datum. Then we'll have all our dimensions coming from that point. So you can see my outside, my longest dimension will be there, and then my shortest, shorter and shortest. try and make my arrows long and thin. Alright, so that would be probably 45. Let's make that 10 and that 20. Alright, so this would essentially be our datum. So that is a much better dimensioning technique than dimensioning each part individually. It eliminates the tendency to accumulate errors when you are dimensioning something that has lots of little features on it. Okay, in your textbook, there's also another part that that's a shaft. So let me just draw a portion of that. And then it gets wider and then a bit narrower. Okay, and just draw a part of it just to illustrate something. So let's just say this is a circular shaft. Need to join up my lines, and if it's circular I will probably put a center line through it. So the center line would go there, and if you remember correctly, our center line is a chain dotted line. Right. So instead of putting dimensions on the outside, we can use diameter dimensions. So we could put a leader line like this and then take it out, pointing to that surface, and we could say that is a diameter of 12. So a circle with a line diagonally through it means diameter. We could do the same here. We could say diameter 20. And we could take this the other way. Yeah, in this case my dimension lines are very close to my part thickness lines. So I really need to make my dimension lines thinner and my part a lot bolder to differentiate. So that would be diameter 10, for example. So there we don't have to draw a side view, an end view showing all the concentric circles, because that drawing tells us that we have circular sections on all three of those. Alright, there's some more information that you need to look at in your textbook about dimensioning, but let's just talk about hatching and sectioning. So sometimes, in order to cut down on the number of views that we show in an orthographic projection drawing, we can cut a section through something. So if we look at the textbook on page 10, we can see we have a component here, which is a bracket with a hole through it. Yeah, we've got a cutting plane, and we've got AA. It's darkened on the edges with arrows to show that it's a cutting plane. That means that the orthographic view looking in this direction would be a sectional view. So we label it as section AA, and we draw what we see looking at that plane and removing everything in front of the plane. So if we're looking from this side, we'll remove everything on this side, and we'll draw what we see on that side. So we'll draw that surface there, we'll draw that hole in the center, and that surface over here, and that little step is on the far side, so we will draw it in as well. All the parts where we've cut through material, we will draw hatching. So that almost looks like a saw has come and cut through the part. So you can think of it as saw grooves, as the saws come and cut through the part. So wherever we have material that's been cut, we've got hatching lines, and wherever we have holes or gaps, then we don't hatch. This is an isometric drawing, It's like a three-dimensional type of drawing where all your axes are at 30 degrees or vertical. And that shows an isometric view of what the hatching would look like. But we don't really do a lot of sectional isometric drawings, at least not by hand, maybe when we get to CAD. So here we have another cutting plane BB cutting through that way, and the arrows show us that we're looking from the top downwards, and we're drawing what we see. If we're looking from the top down and we draw the top view on the bottom, we're drawing in first angle projection because it's on the opposite side to our point of view. Alright, so this is an isometric view of what we've drawn over there. But this is the orthographic projection. So that section there and that section there are the parts of the material that we've cut that we'll hatch, and then the rest of the part below that we'll just draw in normally. So that is how sectioning works. It's showing what's on the inside of the part without having to really cut it yourself. Usually for engineering, for mechanical engineering, we use 45-degree hatching lines. There are some exceptions to that. For example, if you have a part that is being drawn where the part is at 45 degrees, your hatching lines at 45 degrees would look awkward and they won't look random enough, so you'd change the angle of your hatching so that it looks more random. Alright, so you can adjust that angle. When it comes to civil engineering, you may be doing a sectional view through a building which is made of concrete. Then you would draw little stones for your hatching instead of lines, because typically the 45-degree line indicates steel. So that is why it's so common in mechanical engineering and industrial and marine. But in civil engineering, you have lots of different types of hatching lines to indicate different varieties of materials. Right, so there's your projection symbol and there's your scale, 1 to 2. So the most important thing about a sectional view is that you have a cutting plane and you have a labeled view that says section AA. You have to have the two together. If you just draw the sectional view and you don't draw the cutting plane, then it's not clear on the drawing where the part looks like that. Right, so it's important that you show that's the cutting plane and this is what it looks like at that point. So make sure that you have both. You label them as such. So some more information on sectioning. Here we can see different types of sectioning. So here's a half section where we've cut out just a portion, and in orthographic view we will show the outside of one side of the part and we will show the sectional view of the other side of the part. Okay, the other interesting thing is when we are sectioning a rib or a web. Now that is what is shown over here. So it's a reinforcement next to a part. Section AA cuts through that rib, but if we had to section right through the web, it would look like a really thick part. It would over exaggerate the strength of the part. So in that case, we draw it with the outside of the part and with the web unsectioned. Okay, so that's an exception to the rule. So we've got full sections, we've got half sections, and here we have staggered sections. So our cutting plane then jumps from part to part or feature to feature as it goes through, and then you draw your sectional view with all of those holes as though they're in one line. So that allows you to show a lot more information on one drawing. Alright, so here we can see a nice example of a rib that hasn't been sectioned. Keys we don't section, and shafts we don't section. Alright, so here's a list of all the parts that we don't section: bolts, nuts, rivets, shafts, rods, ribs, keys, pins, spokes of wheels, and similar components. So we just show the outside view. There's a nice picture of a bolt. Okay, so the last thing I want to mention in this section is on page 16 through to 19. There's a whole lot of standardized conventions when it comes to engineering drawings, and specifically related to sectioning or showing standard parts, how you draw them. So this is a screw thread, for example, which would look like this in real life, but for simplicity's sake, we only draw a thin line to show the thread depth, and we show the M14, which M refers to metric. That's a 14mm thread. There's gears, there's springs, shafts, etc. So make sure that you go through all of these and make sure you remember exactly how the sections are done and any other information about drawing these specific parts. Alright, so that's all the work that we're going to do in this introduction and drawing standards. So I think we've covered quite a lot today, so have a look at your information on the Moodle site that tells you exactly which exercises you need to go and do, so that you can practice your drawing of your lines, of your lettering, and also start drawing some parts. Alright, so everything is available to you, so make sure you go and practice. Remember, engineering drawing is a skill you have to learn. It's a language you have to learn, and the only way to learn it is by practicing. So go and do all the exercises that are prescribed for you in the outline of the syllabus, that one pager that I've sent to you. I've listed all the exercises you need to do, so those are for practicing. So make sure you do them, so that when it comes around to doing your assessments and submitting work, that you're submitting good quality work because you've already practiced. Okay, we'll see you next time.